In this video we're going to talk about contiguity and chain homotopy. So first let's begin by recalling some of the basic stuff about directly contiguous or generally contiguous maps. So the context is that we've got two abstract simplicial complexes, K and L, and two abstract simplicial maps, F and G, both going from K to L. And we're going to because these are simplicial maps, that means if you've got some simplex sigma in K and you apply F to it, then F of sigma, that's got to be a simplex of L. And because G is a simplicial map, then G sigma also has to be a simplex of L. But that doesn't immediately imply that the union F sigma union G sigma is a simplex. The union of two simplices is not usually a simplex. But the condition for contiguity is like this, that we say that F and G are directly contiguous if for every simplex sigma of K, the union F sigma union G sigma is a simplex of L. More generally, so that was for direct contiguity, and we also consider indirect contiguity. So we say that F and G are indirectly contiguous if we can make a chain of simplicial maps, P0, P1, P2, P3 up to PR, say, such that we start with F and the last one is G, and then for each adjacent pair, Pi and Pi minus 1 are directly contiguous. One basic point about this is F and G are directly contiguous, then the geometric realization of F and geometric realization of G, so there's two different maps from the geometric realization of K to the geometric realization of L, and they're homotopic. In fact, they're homotopic in the most obvious sort of way, just by a straight line homotopy. The kind of point being that if X is some point in a simplex sigma of K, then you apply F to it or G to it, then you apply F to it, then that's in the realization of the simplex F sigma. If you apply G to it, then that's going to be in the realization of the simplex G sigma. And if the union of those two simplices is still a simplex, then you can draw a straight line between those 2 points, between Fx and Gx. That will still lie in the geometric realization of L. So you can do a straight line homotopy between realization of F and realization of G. F and G are indirectly contiguous but not directly contiguous, then it's still going to be true that the realization of F is homotopic to a realization of G, because that's kind of clear, because being homotopic is an equivalence relation, and so each Pi and Pi minus 1 have the same homotopic to each other, so the end things, the P0 and PR are homotopic, or in other words, F and G are homotopic. But in that general case, it's not going to be a straight line homotopy anymore. You're going to have like R different steps, each of which is a straight line homotopy, but when you combine them, it's not going to be a straight line homotopy anymore. But nonetheless, the key point is that the realization of F and realization of G are still homotopic. And so now we're going to prove an extra property about contiguous maps, that if F and G are as before, and if they're contiguous, then we're going to say that the chain maps, F hash and G hash, from the chain complex for K to the chain complex for L, we're going to say that those are chain homotopic. So by a key theorem about chain homotopy that we proved a couple of videos ago, then the induced maps, F star and G star, from the homology of K to the homology of L are actually just the same. So that's what we want to prove. So we've stated this again. So we're going to just do the directly contiguous case first. I mean, the indirectly contiguous case follows in a straightforward way by induction based on the directly contiguous case. So we're going to assume here that F and G are directly contiguous. So that means, remember, that if we've got simplex sigma, V0 up to VR, then the union F sigma union G sigma, that's still going to be a simplex. Okay, so that's going to be that union, of course, that's FG0, FV0 up to FVR, and then GV0 up to GVR, all of those things. So the way we're going to, we're supposed to be proving that the F hash and G hash are chain homotopic. So we need to define a chain homotopy. That's going to be a map S from the R chains of K to the R+1 chains of L. And we're going to do, we need to define it on the generators for the homology of K, of the chain complex for K, which are like this thing here, the pointy bracket V0 up to VR. So the definition is that we apply S to this. You've got a sum of terms indexed I 0 up to I equals R. And in the term number I, you've got a FVI and also a GVI. So these are, of course, all just vertices of L. We've got, as well as the FVI, you've got all the VJs for J up as far as I. You start FV0, FV1, all the way up to FVI. Then you have GVI as well, and then past VI you have G's again. So you've got G of VI plus 1 all the way up to G of VR. Okay. So yeah, in this term indexed by I, you've got FVI and GVI here, and then but the others, the FVJ for other VJs, they only appear once, right? If J is less than I, you only get it with an F. If J is bigger than I, then you only get it with a G. So we're supposed to be proving this is a chain homotopy. In other words, that ds plus sd of x is supposed to be the same as the difference between these two things, g hash and f hash of x. So we're going to have lots of terms to write down, so we need again an efficient condensed notation for it. So our x is just this v0 up to vr. We're just going to do the r equals 3 case here. So our x is v0 up to v3, or 0, 1, 2, 3 as usual. And then so 0, 1, 2, 3, these refer to these vi's, which are vertices in K. And we also got some vertices in L to worry about. So we've got these FVI's, and we're just going to write again I for f of VI. So f of V2, we're just going to be written as 2. But then there's also going to be a G of V2, and to distinguish that from the f of V2, we're going to write it with a bar. So when we're talking about vertices of L, 2 means f of V2, and 2 bar means G of V2. Okay, so let's look at if we look at this definition here again and write it in that notation. S of 0, 1, 2, 3. So you've got this term here where you've got a 0 and then a 0 bar, 1 bar, 2 bar, 3 bar. And then this is the one here where the 1 gets repeated. You have 0 and 1, meaning FZ0, FV1. And then 1, 2, 3 all barred, which is G of V1, GV2, GV3. And then the third term, 0, 1, 2, those are all Fs. And then 2 bar, 3 bar, those are Gs. And finally, this last term here, you've got FV0, FV1, FV2, FV3, and then GV3. And as usual, with alternating signs. Okay, so now we need to calculate ds plus sd of x. Okay, so here's our sx. That's what we just had at the end of the previous slide. And now we're going to do d of it. Okay, so we've written this grouped this in columns. So here we've got this guy here, and then d of it is in this column. This term here and d of that term is in this column. This term here, d of is in this column. This term here, d is in this column. So remember how the d works. Okay, so you've got, firstly we omit this 0, giving this 0, 1, 2, 3 all barred. Then you omit the 0 bar, giving a 0 and a 1, 2, 3 all barred. Then you omit the 1 bar, giving a 0, 0 bar, 2 bar, 3 bar, etc. So we get these 5 terms in d of this term here. And carry on the same sort of way, and then going over to the end here. So you've got here we omit the 0. Okay, so that leaves us 1, 2, 3, 3 bar, and because we've got this extra minus sign here, so you get an overall minus. And then the next term down here, if you omit the 1, you get 0, 2, 3, 3 bar like that. And you've got this minus sign here, but also a minus sign because it's like I equals 1 in the definition of D, so that will give you an extra minus. It's 2 minuses, which is a plus. And you carry on down here. The very last term you get is where we omit this 3 bar from the end, and you've just got a minus 0, 1, 2, 3. And we're going to regroup it like this. Okay, so and there we've done the most obvious kind of grouping with all the terms in D of this here, all the terms in D of this here, etc. But we're going to regroup it like this. Okay, and so you can already see some kind of cancellation going on now. These in this red region here. You've got a minus 0, 1, 2, 3 bar, plus 0, 1, 2, 3 bar, a minus 0, 1, 2 bar, 3 bar, plus 0 and 2 bar, 3 bar, etc. So these terms cancel, these terms cancel, these terms cancel. But then you've got all these terms here and these terms here that don't already cancel. But that was just dsx. And remember, we're supposed to be thinking about ds plus sd. So let's think about sd. So dx, okay, x was just our 0, 1, 2, 3. You apply d to it, you get plus 1, 2, 3, minus 0, 2, 3, plus 0, 1, 3, minus 0, 1, 2. And then then we apply S to that. Okay, so we've grouped this like here. We've got the 0, 1, 2, 3, and apply S to that. So you get the 1 and then the 1, 2, 3 all barred. And then over here you get the 1, 2 and then the 2, 3 all barred. And then the 1, 2, 3 and the 3 barred. And so on and so on. And that's it. And then you get this last term here. When we apply S to this, you get the 0, 0, 1, 2 all barred. Then you get 0, 1, 1, 2 all barred. And 0, 1, 2 and the 2 barred. Okay. And we've regrouped that. Just divide this into two groups, and what we find is that it pretty much matches up with what we had over here. Okay, so so you find that everything here is the same as everything here, except here except for the signs are opposite. So everything in this group is going to cancel against that. Everything in this group is going to cancel against that, and everything in these red lozenges here they just cancel internally, and so all that's left is this one here and this one here. So you get ds plus sd of this x is 0, 1, 2, 3 all barred minus 0, 1, 2, 3. Notice that, remember, this is all happening on the right hand side. This is all in the chain complex for L, and so the 0, 1, 2, 3 they mean f of v1, 0, fv1, fv2, fv3. The barred ones are gv0, gv1, gv2, gv3. So if you go back to the original notation, what this equation here is telling us, ds plus sd of x, you've got the thing with a g applied minus the thing with f applied, and that's the same here. This is g hash of our original x, and this is f hash of our original x. So what we've got is that ds plus sd of x is g hash minus f hash x, and we only did that for r equals 3, but it should be clear that it works the same way for any r. So that means that S is a chain homotopy between f hash and g hash. That was our definition of what a chain homotopy means, that ds plus sd should be the difference between the two things. And we also proved a while ago that if you've got chain maps that are chain homotopic to each other, then they induce the same homomorphism in homology. Okay. And so that completes the proof for the case where f and g are directly contiguous. But if they're indirectly contiguous, then it just means you've got a whole chain of things, P0, P1, P2, all the way up to PM, say, where each one is directly contiguous to the next, and so they all just have the same effect in homology.